Welcome to the lecture series on CFD Part 1. This is lecture 11 on advanced solution methods for linear algebraic equation systems. In this lecture, we shall first discuss the under-relaxation approach. Its aim is to promote the convergence of outer iterations when solving nonlinear and coupled equation systems, but it is also important when deferred correction approach is used in conjunction with discretization methods of a high order. Because it modifies the linear algebraic equation system and thus influences also the performance of linear equation solvers, the under-relaxation approach, which is widely used in CFD, is described first. Conjugate gradient types of solvers are then briefly described. The mathematics behind these methods is too complex for most engineers, including myself, so the algorithms for three solvers are described without derivation. Two of these methods, one for symmetric and one for non-symmetric coefficient matrices, will be tested in the next lecture, and the codes will be available in source form in supplementary material for lecture 12. Finally, multigrid approach is described in more detail. It can be applied to accelerate any iterative solver, which will be demonstrated in the next lecture. It is not guaranteed that every iterative solution method will converge under all circumstances. Convergence problems often occur when one or more of the following conditions are present. The linear algebraic equation system represents linearization and decoupling of a nonlinear coupled equation system, which is the case in Navier-Stokes equations. The deferred correction approach is used to simplify the matrix of the linear algebraic equation system, for example, to limit it to reference only the nearest neighbors of each grid node when using high-order discretization methods. In this case, even a linear equation system requires outer iterations to update the right-hand side, even though the coefficient matrix is not updated. And the grid properties are not optimal. For example, high non-orthogonality, high aspect ratio, etc. Under-relaxation is a widely spread approach to improve the convergence properties of iterative solution methods. Here, the method used in most CFD codes is described. The aim of under-relaxation is to limit the change in variable values from one iteration to the next in a way that increases the diagonal dominance of the iteration matrix. On the nth outer iteration, the linear algebraic equation for a generic variable phi at grid point P reads like this. P denotes the grid point or control volume center at which the variable value phi p is to be computed, and the summation is over all neighbor grid nodes or cell centers from the computational molecule, typically the nearest neighbors. QP contains all terms which do not depend on the solution phi n, but both QP and the coefficients of the matrix A may involve the solution from the previous outer iteration because of linearization. Allowing phi to change from iteration n-1 to n as much as results from the above equation may lead to divergence of outer iterations. To prevent that, we allow phi to change only a fraction alpha phi of would-be difference. Here, phi nu is the solution of the above equation without under-relaxation. This equation shows the implicit expression for phi p nu resulting from the algebraic equation at node P. When we insert this expression into the under-relaxation formula, we obtain after some rearrangement the following modified algebraic equation. AP star and QP star are modified main diagonal element and source vector component respectively. Because the original values of AP and QP are no longer needed, the modified values overwrite them, and the modified equation looks the same as the original equation given here. The under-relaxation factor takes values between 0 and 1. When the outer iterations converge, the terms from the previous equation involving alpha phi cancel out, and the solution satisfies the original equation. This kind of implicit under-relaxation was proposed by Patankar in 1980. It is the standard approach of promoting convergence of outer iterations in all CFD codes. Although primarily aimed at improving convergence of outer iterations, that is, the number of updates of the coefficient matrix A and the right-hand side Q, this kind of under-relaxation also has a positive effect on convergence of inner iterations. Under-relaxation increases the diagonal dominance of the modified equation system because the element on the main diagonal is enlarged by division with alpha phi smaller than 1, while other elements remain unchanged. Optimal under-relaxation factors are problem-dependent. Convergence becomes faster as alpha phi is increased up to a certain value, beyond which divergence may occur. Examples will be shown in the next lecture. Conjugate gradient type solvers convert the original system of equations into a minimization problem. For a positive definite matrix A, solving the original equation system A phi equal Q is equivalent to finding the minimum of the following function with respect to all phi I. The oldest and best known method for seeking the minimum of a function is steepest descent. From a starting guess, we follow the steepest downward path on the function surface in the direction opposite to the gradient of the function. Steepest descent solvers often do not converge well. They tend to traverse across narrow valleys, as shown by the red line in this figure here. This means that the same search direction is used repeatedly. An improvement is provided by the conjugate gradient method, which minimizes a function with respect to several directions simultaneously while searching in one direction at a time. Each new search direction is required to be conjugate to all preceding ones. The method is guaranteed to converge in a finite number of steps, but it may take many iterations before optimal search directions are found. We need a solver which quickly improves the solution sufficiently for one outer iteration. Conjugate gradient methods are made more efficient by preconditioning, that is, by multiplying the system by another matrix such that the condition of the resulting matrix is improved. Here is the algorithm of a preconditioned conjugate gradient solver. The solution process is started by initializing the solution vector with phi in, computing the initial residual vector rho 0, setting the initial search vector p0 to 0, and setting s0 to a large number, for example 10 to 30. We then advance the iteration counter by 1 and solve the system matrix M times vector z equal residual vector rho from the previous iteration. M is the iteration matrix which depends on preconditioning. Often it is the incomplete Cholesky factorization of matrix A, but on structured grids the incomplete lower upper decomposition after stone leads to better performance. In the next step, a dot product of vectors rho k-1 and z is computed, followed by the computation of the ratio of sk over sk-1, which is denoted beta. The new search vector pk is then computed as the sum of vectors zk and p from the previous iteration times beta. Next, we compute the vector resulting as the product of the matrix A and the vector pk and perform a dot product of that vector with the vector pk. Sk divided by this result is denoted as alpha k. Finally, the solution vector is updated by adding to the value from previous iteration the product of search vector pk and alpha k. Then the new residual rho k is computed by adding to the residual from the previous iteration the product of a pk multiplied by alpha k. These steps are repeated until the residual norm falls below the specified threshold, assuming that iteration errors have fallen to a similar level relative to their initial values. The incomplete Cholesky preconditioned conjugate gradient method, often called ICCG, can be applied to symmetric matrices resulting from discretization of Laplace or Poisson equations, for example, pressure or pressure correction equation for incompressible flows. The ICCG solver will be used in test cases presented in the next lecture and will be available in source form in supplementary material for lecture 12. For equation systems involving non-symmetric matrices, as resulting from discretization of any convection diffusion equation, the method needs to be extended. In the next two slides, two such extensions will be presented: B-conjugate gradients method and CG-stub algorithm. CG-stub solver will be used in test cases presented in the next lecture and will be available in source form in supplementary material for lecture 12. To be able to solve equation system in non-symmetric matrices, we must convert the asymmetric problem to a symmetric one. One possibility is shown in this equation. We have here an auxiliary vector psi, which is never computed, and the transpose of the matrix A. The algorithm of the B-conjugate gradient solver goes as follows. The solution process is started by initiating the solution with phi initial, computing the initial residual vector ρ0 and ρ0 bar, and setting the search vector p0 and p0 bar to 0, and s0 to a large number, say 1030. We then advance the iteration counter by 1 and solve systems matrix M times vector z equal residual vector from the previous iteration, and similarly with the transpose. M is the iteration matrix which depends on preconditioning. In the next step, a dot product of vectors ρ bar from previous iteration and z is taken. The product is denoted as sk. This is followed by computing the ratio of sk and sk minus 1, which is denoted as beta. The new search vector pk is then computed by adding to the vector z the product of beta and the search vector from previous iteration. The same is repeated for p bar. Then the product of the matrix A and the search vector pk is computed, and the dot product with pk bar is taken. The ratio of sk with this resulting product is denoted as alpha k. Finally, the solution vector phi k is updated by adding to phi k minus 1 the search vector pk multiplied by alpha k. This is followed by updating the residual ρ k and ρ k bar, following these expressions. These steps are repeated until the residual norm falls below the specified threshold, assuming that iteration errors have fallen to a similar level relative to their initial values. The computing effort is twice higher than with the method for symmetric matrices. The method is robust and applicable to both structured and unstructured grids. The algorithm of CG stub solver goes as follows. The solution process is started by initializing the solution vector phi with phi in, computing the initial residual ρ0, and initializing vectors u and p with 0. We then advance the iteration counter by 1 and compute beta k as a dot product of the initial residual vector with the residual vector from previous iteration k minus 1. Next, omega k is computed following this expression. The new search vector is computed next from this expression using residual vector from previous iteration and search vector pk and the auxiliary vector uk from previous iteration with multipliers alpha k minus 1 and omega k. We then solve the system matrix M times vector z equal search vector pk. M is the iteration matrix which depends on preconditioning. Next, we compute the vector uk as the product of the matrix A and vector z. We then take the dot product of uk and the initial residual vector ρ0, and the ratio of beta k with this product is denoted as gamma k. An auxiliary vector w is then computed as the residual vector from previous iteration minus gamma k times vector uk. We then solve the system matrix M times vector y equal vector w and calculate vector v as the product of the matrix A and vector y. The ratio of the scalar products of vectors v and ρ k and vector v with itself is denoted as alpha k. Finally, the solution vector phi k is updated by adding to the value from previous iteration the product of gamma k times z vector and alpha k times y vector. The residual ρ k is updated as vector w minus alpha k times vector v. These steps are repeated until convergence. The computing effort is lower than for bi-conjugate gradient method. The method is robust and applicable to both structured and unstructured grids. For most iterative solvers, iteration errors consist of a mixture of smooth and rough components. The rough components are relatively quickly smoothed out, but removal of components with a large wavelength relative to grid spacing requires many iterations. The lowest resolved wavelength corresponds to 4 delta x, and the highest is twice the width of the solution domain. To demonstrate the main idea behind multigrid strategy, consider steady one-dimensional heat conduction problem, given by this equation. We consider different initializations, with initial field being equal to iteration error because the exact solution is zero values at all grid points. We use the simplest iterative solver, the Jacobi method. The partial differential equation from previous slide is discretized by central differences, leading to this expression. When Jacobi solver is used, the new value at node I is computed as the average of the old values at the nodes I-1 and I+1. With both boundary values being 0, the exact solution is zero field in the whole solution domain. Consider two initializations according to these figures. In one case, the initial error oscillates with the highest frequency resolvable by the grid. In the other case, the initial error varies linearly from the maximum value at the center to zero values at the two boundary points. Applying Jacobi solver leads in the first case to the exact solution already in the first iteration, while in the second case the solution is changed only at the middle point. In the following iterations, only the corners are being cut, like when cutting kebab slices. Many iterations are needed to reduce this error component to zero level. The main idea behind multigrid method is that a smooth error field can be faster reduced on a coarser grid. Computations on a twice coarser grid are much faster, 8 times in 3D, 4 times in 2D. In addition, most iterative solvers converge faster when the grid is coarser. For example, Gauss-Seidel solver is 4 times faster on a grid with double spacing, in 2 dimensions. If we solve the original discretized equation on a coarser grid, we get a different solution with larger discretization errors. What we want is to improve the fine grid solution by relegating some work to coarser grids. Therefore, we must solve different equations on the coarse grid, not A times phi equal Q, but A times epsilon n equals rho n, where epsilon n is the error or correction, and rho n is the residual from iteration n on the fine grid. The source of iteration error is the residual. When it is 0, the error is also 0. To solve the equation for the fine grid iteration error on the coarse grid, one needs to construct the matrix A on the coarse grid and transfer the residual from fine to coarse grid. For non-zero residuals, the coarse grid will return a correction which can be added to the fine grid solution. The following terminology is common in multigrid community. Smoothing the node's iterations on a given grid using an iterative solver. In principle, any solver can be used. Restriction denotes transfer of variables from fine to coarse grid. When solving linear equation systems, only residuals need to be transferred from finer to coarser grids. Prolongation denotes transfer of variables from coarse to fine grid. Only the correction for the fine grid variable, that is the estimate of the iteration error, needs to be transferred from coarser to finer grids. In finite difference methods, the coarse grid normally contains every second line from the fine grid. In finite volume methods, coarse grid is usually constructed by merging control volumes from the fine grid, 4:1 in 2 dimensions, 8:1 in 3 dimensions. These two plots show common multigrid patterns in finite difference and finite volume methods. In principle, grids can be both non-uniform and non-orthogonal, as indicated by the finite volume cell shown here. In finite volume methods, the right-hand side of the discretized equation represents in principle the volume integral of the source term. It is thus natural to sum the residuals from fine grid cells to define the residual on the coarse grid. The coefficient matrix on the coarse grid is built by discretizing the original equation on that grid. Field variables which may be needed to construct the coefficient matrix, for example velocities needed to compute the mass fluxes, can be interpolated using linear or high-order interpolation methods. In finite difference methods, integration is not used, but it still makes sense to determine the residuals at coarse grid nodes, black symbols in this figure, such that the sum of residuals on the coarse grid equals the sum of residuals on the fine grid. Field variables, for example velocities for convection terms, are simply injected, that is, the value from the fine grid at the same node is used at the coarse grid as well. The coefficient matrix is built by discretizing on the coarse grid, considering double spacing. These are just straightforward options. There are many more possibilities. The correction computed on the coarse grid represents a field variable which can be interpolated in space. In finite volume methods, the location of coarse grid cell centers, where the correction is computed, and fine grid cell centers, to which the corrections need to be transferred, never coincide. Therefore, interpolation between 4 coarse grid cell centers is used to determine the values at 4 fine cell centers, as indicated in the figure. In finite difference methods, some grid nodes coincide in fine and coarse grids, and the correction computed on the coarse grid node is injected into the coinciding node on the fine grid. For non-coinciding fine grid nodes, interpolation must be applied. In principle, linear or any high-order interpolation can be used. The coefficient matrix on the coarse grid can be generated in many ways. Geometric multigrid methods use the matrix from discretized equation on the coarse grid. In algebraic multigrid methods, the coarse grid matrix is obtained from fine grid matrix by algebraic averaging techniques. Geometric multigrid is usually used in CFD to accelerate outer iterations, that is, to update coupling and nonlinearities, and almost always on structured grids. Algebraic multigrid methods are usually used to accelerate solution of linear equation systems, that is, inner iterations, on unstructured grids. Almost all commercial CFD codes use algebraic multigrid methods to solve linear equation systems, at least for the pressure correction equation. One also needs to define how many iterations should be performed on each grid before moving to another grid level. The 2-grid procedure is outlined in the next slide. This is the sequence of operations in a 2-grid multigrid procedure. On the fine grid, perform some iterations on the original equation with a solver that gives a smooth error. Then compute the residual on the fine grid. Restrict or smooth the residual to the coarse grid. Perform some iterations on the correction equation on the coarse grid using a coarse grid approximation of the matrix A. Then prolong or interpolate the correction to the fine grid. Update the solution on the fine grid by adding the correction to the latest iterate. And repeat the entire procedure until the residual is reduced to the desired level. The optimal number of iterations performed on each grid depends on the linear equation system used, the problem being solved, and on grid properties like aspect ratio and non-orthogonality. An example will be shown in slide 23. The 2-grid procedure just described can easily be extended recursively to still coarser grids. It is desirable to have the coarsest grid very coarse, so it is not unusual to have 10 or more grid levels involved and the coarsest grid containing only a few cells. There are many possible patterns for grid sequencing: V cycle, W cycle, F cycle, etc. Which cycle is the most optimal is not easy to guess. In any case, the difference in performance of various cycles is by far much smaller than the difference between single grid application of the linear equation solver and the same solver being used within a multigrid algorithm. The most important property of multigrid methods is that the number of iterations required to reach certain accuracy is independent of the number of grid nodes or control volumes. This means that the computing effort increases linearly as the grid is refined, which is the optimal convergence property. The initial solution is usually far from being accurate. Usually it is zero or another constant field. It therefore makes sense to first solve equations on a very coarse grid and use the result to initialize the solution on the next finer grid. From 2-grid onwards, we can use the so-called full multigrid method. The cost of obtaining coarse grid solutions is more than compensated for by savings on the finest grid. Examples will be shown in the next lecture. The full multigrid or FMG procedure looks like depicted in this figure. we first obtain a converged solution on the coarsest grid. The result is prolongated to the next finer grid, where we perform several iterations on that grid and then start a two-level multigrid procedure. Residuals are restricted to the coarsest grid, and after a few iterations there, we obtain an estimate of the fine grid iteration error or correction. This correction is prolongated to the level 2 grid and added to the solution, and this V cycle is repeated until a converged solution is obtained on grid level 2. The result is prolongated to grid level 3 and used there as the initial solution. After a few iterations, we initiate a free-level multigrid procedure with V cycle and repeat the sequence until convergence, and so on until the finest grid is reached. The numbers in circles here indicate how many iterations are performed at each grid level. You see that the number of iterations is increasing from the finest to the coarsest grid level. Because iterations at coarser grid levels are much cheaper than iterations on the finest grid, we try to minimize the number of iterations on the finest level. Obviously, one iteration is the minimum, and often it is enough, but under some circumstances these numbers may have to be increased. The multigrid procedure described so far represents the so-called correction scheme, which is applicable to linear equation systems, that is, inner iterations. When residuals on fine grid are set to 0, the coarser grids should return 0 correction. Approaches for using multigrid procedure to accelerate outer iterations will be described in the second part of the course. Let me briefly summarize this lecture. Solvers of conjugate gradient type have advantages over other iterative solvers. They are more robust and do not have parameters that require tuning. They usually converge in fewer iterations. The increase in the required number of iterations to reach specified accuracy with grid refinement is less pronounced, and they are applicable to both structured and unstructured grids. Multigrid methods speed up convergence of every iterative solver, including conjugate gradient type solvers. This will be demonstrated in the next lecture. Multigrid method requires the same number of iterations to reach the prescribed accuracy on any grid. The efficiency of multigrid method depends on the iterative solver used, grid properties, and the problem being solved.